right, so what we're going to be looking today at is an aspect of relations called partial orders. And what partial orders allow us to do is they allow us to construct a structure on relations, and this particular structure is called a partial order. And you'll see that oftentimes when we look at, say, for example, real numbers, integers, that sort of thing, they have already on them one partial order or maybe several partial orders. So let's first start out with the definition of a partial order. One, we define the relation R on our domain A. And to be a partial order, we have to have three relationships. One, it has to be reflexive. Two, the relation has to be antisymmetric. And three, the relation has to be transitive. Now, if there's a partial ordering on R, we say that X, R, Y is written as, and we've got this symbol right here, and what we say is that X is at most Y. So when we hear the phrase X is at most Y, we're thinking about this like little curvy less than or equal to sign. Just to kind of review our terms, what we have here is that R is reflexive if XX belongs to R for all X and A. And so from the perspective of a digraph, that means that every single one of our vertices will have a self-loop. R will be antisymmetric if we have, when X does not equal Y, if XY belongs to R, then YX is not going to belong to Y. So what that means, belong to R. And so what that means for us is that no edge in the graph has another edge going in the opposite direction. 3, R will be transitive if when XY belongs to R and YZ belongs to R, then XZ is going to belong to R. So if we have an edge from X to Y and Y to Z, then we're going to have another edge that goes from X to Z on our digraphs. Looking at this, let's say we have this particular digraph, and we notice we've got the 4 vertices, 1, 2, 3, and 4. You'll notice that each one of them has a self-loop, 1 to 1, 2 to 2, 3 to 3, 4 to 4. Then we can see that if we go from 4 to 3 and 3 to 1, then we're also going to have one that goes from 4 to 1. Right? And that's transitivity. You'll notice that we don't have any other edges here, and just those 3 edges, all 3 of those edges demonstrate transitivity. Finally, we have antisymmetry. You'll notice that if we have anything other than a self-loop, we don't have any of the other directions. So we don't have a direction that going backwards from 3 to 4. That doesn't work. It's not on there. And so consequently, we can see that we have an antisymmetric relation. Look at another example. Let's say we have this set R. It's got AA, AC, BA, BB, BC, and CC. One, we'll notice that we have our reflexive elements, AA, BB, CC. We'll also know, other than those reflexive elements, we've got AC, BA, and BC. Notice no CB, no CA, and no no AB. We don't have any of those relationships, so that's antisymmetric. That's our example there. And then we'll see, let's take a look at the other ones. We have AC, we have BA, we have BC. So if I have if I have BA to AC, okay, then that gives me also BC, and so that gives me that I have transitivity. So what that gives me a partial order. Looking at an example from math, this is really a common one. This is probably our most famous partial ordering, and that is X is related to Y if X is less than or equal to Y. We'll notice that if X equals X, then X is less than or equal to X, and X is less than or equal to, well, X. There you go. So reflexive, that's reflexivity. I mean, I guess we don't even need the second one right there. That's not even necessary. On the other hand, if we have X is related to Y, that means X is less than or equal to Y. So Y is not less than or equal to X unless, right, X equals Y. So that's our antisymmetry. And if X is related to Y and Y is related to Z, then that means that X is less than or equal to Y, Y is less than or equal to Z, so given X has to be less than or equal to Z. All right? So X is related to Z, we have our transitivity. So you could see less than or equal to, our less than or equal to sign, is also a partial ordering, although it's not the only one. Clearly we've done a couple others already. Let's look at one more. Let's say, for example, we have A equals 1, 2, 3, 6, and 9. and we define R as XRY if X divides Y. And so, for example, we know, we'll draw a little digraph here. Let's say we have 1, 2, 3, 6, and 9. We know that 1 divides 2, 1 divides 3, 1 divides 6, and 1 divides 9. We already know those. We know that also that 2 is going to divide 6. We know that 3 will divide 9, and we know that 3 will divide 6. And we also know that it's not going to go the other way around. We know that, for example, 6 will not divide 3. That's going to give me 1/2. We know that 9 will not divide 3, so we don't end up getting any of those backwards loops. That's actually going to tell me that I'm going to be anti-symmetric. But we also know, for example, that 1 divides 1. 2 divides 2, right? Because 2 divided by 2 is 1. 3 divided by 3 is 1. 6 divided by 6 is 1. 9 divided by 9 is 1. Now notice on our digraph that if 1 divides 2 and 2 divides 6, we also have 1 dividing 6. And by the way, that's really the case because it turns out that 1 divides everything. So like in this particular case, it works out really quite easily. Now let's talk about another kind of, and that is this idea of being comparable and incomparable. So we're going to say that X and Y are comparable if X is at most Y or Y is at most X. So it doesn't really matter what the relationship is there, like which one happens to be the at most one. It only matters that in the case of the two elements, one or the other is at most the other. So it actually exists inside of the partial ordering with each other. Otherwise, we're going to say that X and Y are incomparable. So if every element in A is comparable, then R is called a total order. In the case of, say, for example, less than or equal to, that is a total order. Because if you think about it, if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C, right? And if we have A, any element A is going to be either less than or equal to another element in the set, or it's going to be greater than or equal to the other element in the set. And so that element is going to be less than or equal to A. So you kind of see that inside of the less than or equal to, we have what's called a total order. On the other hand, if we look at X divides Y, this is not a total order. For example, 6 and 9 are not comparable. 6 does not divide 9, 9 does not divide 6, so consequently, that's not a total order. Let's look at another vocabulary idea. Really important vocabulary idea is this idea of minimal and maximal elements. Now, inside of our less than or equal to or greater than or equal to, the idea of minimal and maximal makes a lot of sense. Minimal is the smallest number inside of the set. Maximal is the biggest number inside of the set. But remember, we can have a lot of different kinds of orderings. So it turns out that we can have more than one maximal or minimal element. And we can have plenty of elements that are neither maximal nor minimal. So let's first define it and say that a minimal element of a partial order is if there's no y not equal to x, such that y is at most x. So that's basically the idea that there's no y that's less than or equal to x. We don't have x as what we'd say a head inside of any one of our edges. X is a maximal element of a partial order if there's no y not equal to x, such that x is at most y. And what that means is that there is no element that is bigger than x. X is the quote-unquote largest element. Now, if two elements are not comparable, they could actually both be maximal elements, or they could both be minimal elements. And that's one of the reasons why it's so important to understand what happens when we have orderings where not everything's comparable, because we can have multiple maximal and minimal elements. And I'll give you an example in just a second. Let's take a look at this first example. We have ABC, okay? And what we're going to say here is that for a minimal element, minimal elements are never tails. Well, never tails except in a self loop. So inside of the reflexive element, right, the AA, the BB, the CC, yeah, it'll be a tail there. However, anywhere else it can actually be a tail, and that's because what we basically don't want to have is, say for example, we look at B here. We notice that B is at most A and B is at most C, but C is never at most B and A is never at most B either. right? Those are the other two elements. So B is the minimal element. It's always essentially the head. In terms of a maximal element, it's never a head. In this example, we'll notice that we do have A is at most C, right? So not A, but we'll never get C as at most A or C is at most B. That never happens. Neither one of those occur, and so consequently, C is the maximal element in this set. So that's a case in which we have one minimal element, one maximal element. And what we want to notice also here, this is a total order. We have some kind of relationship between all of them. Now, on the other hand, let's take a look at x, r, y if x divides y with our set A. In this case, what we want to notice is that everything divides either 6 or it divides 9, but 9 doesn't divide anything and 6 doesn't divide anything. So 6 divides x, that doesn't occur. 9 does not divide x, so that doesn't occur. So that means that 6 and 9 are both maximal. They don't actually go through and divide anything. On the other hand, 1 divides every single element inside of the set, right? So 1 divides 2, 1 divides 3, 1 divides 6, 1 divides 9, and nothing divides 1. It's very important. Nothing divides 1. That's actually the most important part, most important aspect. So 1 is the minimal element. So in the case of this particular relation and this particular partial ordering, we have 2 maximal elements, 6 and 9, and 1 minimal element. Right? Kind of different. Also notice, this one here, not a total order. The elements are not all comparable, and that's actually what allows us to have both a minimal and a maximal element. Let's now look at something called a Hasse diagram. And this is, or an upward drawing, and it's a way of drawing partial orderings. First, all the lines of the diagram we're going to move upward, so we're going to get no arrows. If there is no line connecting to a vertex from below, then the two elements are not comparable. And I should actually add one more thing, that if we have transitivity, so if we have 3 transitive elements, we will only draw a line to the middle element. This allows us to preserve that upward movement of the upward drawing or the Hasse diagram. So like for example, if I have 1 is at most 3 and 3 is at most 5, okay? I know I do have 1 is at most 5, but what I'm going to do is I'm going to draw a line from 1 to 3 and 3 to 5. And then my reading of the Hasse diagram says, oh yes, because this is a partial ordering, there must also be an edge from 1 to 5. It's inferred rather than actually drawn on the diagram. Let's take a look at an example. Let's say, for example, I've got this digraph here. So in this digraph, we'll notice that 4, everything's coming out of 4. 4 ends up being the minimal element. So I'm going to put 4 at the bottom here. And 4 will go to 3. And 3 will go to 1. And the reason why is because if you kind of imagine what we've got here, our transitivity goes from 4 to 3 and 3 to 1, even though we do have a line from 4 to 1. Notice that it's not 4 to 1, 1 to 3. We could do something like that, but not in this particular ordering. And then if we look at 2, there's nothing actually that goes into 2. 2 is all by itself, so inside of our diagram, we're just going to put 2 going all by itself. What that tells me is that 2 only has a self loop. The self loops for 1, 3, and 4, they're all inferred. And even though we don't have a line from 4 to 1, we know that because we only draw Hasse diagrams for partial orderings, there must also be an edge from 4 to 1. It basically shows us the relationships between our elements. Now, in addition to that, it's also going to show us our minimal and maximal elements. 4 is a minimal. It's at the bottom. Everything comes out of 4, nothing goes into 4. 1 is a maximal element. Everything goes into 1, nothing comes out of 1. 2, on the other hand, is both maximal and minimal. It's both maximal and minimal because there's nothing that actually goes into 2 or nothing that comes out of 2, right? It's just off on its own. Let's take a look at another example. So let's say, for example, we have this x divides y, and what we'll do is we'll notice, okay, well, remember that 1 is our minimal element. And we have 1's going to go to 2, 1 goes to 3, 1 goes to 6, and 1 goes to 9. Now here's the thing, 2 and 3 are not comparable, so what we're going to need to do is I'm going to need to draw one line to 2 and one line to 3. Inside a Hasse diagram, if two elements aren't comparable, we don't actually have a line adjoining the two of them, and that's because all of those lines happen to be only going upward. Now, what we'll do is we'll draw 3 goes into 6, and we'll note that 2 also is going to go into 6. That's just fine. And then I'll have another element, 3 going into 9, showing us that 3 is related to 9. Again, we don't have lines going from 1 to 9. We don't have lines going from 1 to 6 because our transitivity to 9 goes through 3. Our transitivity to 6 goes through 2, so it's assumed that we actually have that relationship. Notice also that the upwardness, it kind of goes along a diagonal. That's just fine. That's not a problem. Okay? And we get, for example, that 1 is at most 2 and 2 at most 6. We also get 3 is at most 6 because we've got an upward line connecting to 6. And then the transitivity for both 1 and 2 going into 6 is just assumed in the Hasse diagram. Again, we can tell which ones are minimal elements and which ones are maximal elements. In a Hasse diagram, the minimal one's pretty easy to tell. It's the bottom. There's our minimal. Our maximals are going to be the ones that have nothing coming out of them. So these are our maximal elements in the Hasse diagram. In addition to that, we can tell if two elements are comparable if there is a line that either goes directly up or directly down from that element. If they're sideways from each other, like 2 and 3, okay, no way in between and out, that means that we have incomparable elements. Same thing with 6 and 9, for example, they're also incomparable. And that's how we work with Hasse diagrams or upward diagrams. They're actually, once you learn how to read them, get a little bit of practice with them, they can make understanding partial orders a lot easier, because sometimes partial orders aren't really all that intuitive. They're a little harder to understand. Let's review our basic ideas. One, we have that a relation is a partial order if R is reflexive, R is symmetric, and R is transitive. Now, if X is at most Y or Y is at most X, we say that X and Y are going to be comparable. Also, if we have for all Y, X is at most Y and X does not equal Y, then X is a minimal element. If Y is at most X and X does not equal Y, then when X does not equal Y, then X is a maximal element. So posets, which are these partially ordered sets, can have more than one minimal or maximal element. We want to remember that. And then a Hasse diagram allows us to easily draw the relationships between elements in a poset and show the flow or the ordering of those elements inside of that poset. Hey folks, I hope you enjoyed learning about partial orders and relations as much as I did. If you did, please go ahead and click on the thumbs up. If you want to leave a comment, or you have a question, or there's something that you maybe want to learn a little bit more about, especially with regards to partial ordering or relations, please go ahead and leave me a comment. If you like all the work that we're doing, you want to learn more about relations, you want to learn more about discrete mathematics, you want to learn more about linear algebra, differential equations, calculus, whatever, go ahead and subscribe to the channel.